Okay, hi. And the third topic to be discussed under game theory subject is games with simultaneous moves. And to be more precise, this time we're gonna concentrate only on pure strategies and discrete strategies. So pure strategy means that neither of the agent randomizes, in contrast to the games with mixed strategies. And discrete strategies means that there is a finite number of possible strategies. So they are not described in the continuous ways as the function. Instead, we just have discrete strategies. Okay, so as we discussed before, normal form of the game or payoff matrix is a common way to analyze games with simultaneous moves. So in row, you also have strategies available for the first player. In column, you have the strategies available for the second player. The sequence of payoffs is first payoff for the first player, here payoff for the second player. Okay, when it comes to defining solution for the games with simultaneous moves, Nash equilibrium is the most frequently used concept. So, speaking informally, Nash equilibrium occurs when all the players pursue their optimal strategies, keeping in mind that other players do the same. More formally, Nash equilibrium in a game is list of strategies, one for each player, such that no player can get a better payoff by switching to some other strategy that is available to her, while all the other players adhere to the strategy specified for them in the list. Speaking very informally, in Nash equilibrium, if the second player does not change his strategy, the first player will not do this as well, and vice versa. You will see this in a second. Again, consider this game. We're gonna solve it using best response analysis, and the idea behind best response analysis is that we try to figure out the most adequate response for each player constrained to the strategy pursued by the other player. So for instance, imagine that the column player decides to choose left. Then the row player can choose top and get 3, high and get 4, low and get 2, or bottom and get 5. Like obviously here 5 is the optimal solution, so that's why we can circle this. If the second player decides to go middle, then going low would be the most adequate response of the row player. And finally, if the second player decides to go right, in this case, the first player would prefer to go low because payoff associated with combination of right and low is higher than payoff associated with right and any other strategy available for the first player. Now we can analyze, do the same analysis for the column player. If the first player decides to go top, then the first player can go left and get 1, middle and get 3, or right and get 2. Obviously, the second player will decide to go middle. If the first player, row player, decides to go high, then the second player can go left and get 5, middle and get 0, or right and get 4. 5 would be the most preferable option. If the first player decides to go low, then the second player can go left and get 2, middle and get 4, or right and get 3. In this case, middle will provide the highest payoff. Finally, if first player decides to go bottom, then the column player can go left and get 6, middle and get 5, or right and get 7. Obviously, 7 is the maximum available payoff in this case. So this is called best response analysis because basically we analyze, the best response of each player to any strategy which might be pursued by the other player. And on the intercept of those strategies, we have middle and low. So basically here we exactly have the Nash equilibrium, a situation which occurs when two players pursue their best strategies simultaneously. Also, please take a look. Like, once we are in this cell, and since we have no reasons to expect the second player to deviate from middle, there are no reasons for the first player to change her strategy as well. So the first player can change from low to bottom and get 4 instead of 5. The first player can shift to high and get 3 instead of 5, or top and get 2 instead of 5. So neither of these options does not make any sense for the first player, because it will result in the decrease of payoff for the first player. The same for the second player. Like, the second player can shift to left and get 2 instead of 4, or the second player can shift to right and get 3 instead of 4. Again, there are no reasons to expect the second player to change her strategy. That's why actually this is equilibrium, Like, basically in economics, equilibrium is a situation in which neither of the variables is likely to change unless there are some changes in external environment. And we can observe the same here, So the first player has no reasons to expect the second player to change his strategy, and that's why there are no reasons for the first player to change her strategy, and vice versa. Also, please keep in mind that this outcome is not Pareto efficient. Very informally, you can define Pareto efficiency as a situation in which neither of the players can get a higher payoff without worsening payoff of the other player at the same time. Here, it's not true. It's possible to improve situation of the first player and the second player simultaneously if they shift from low middle to bottom right. Then first player gets 9 instead of 5, and the second player gets 7 instead of 4. However, such a change would require some cooperation between those players. Which is not assumed, because we assume simultaneous games with the lack of interaction and with no awareness about decisions made by the other player. Moreover, there are also incentives to deviate. So let's say that those players made an agreement, so they agreed that the second player will choose right and the first player will choose bottom. So actually in this case, for the first player, there is always a temptation, to betray and choose low instead of bottom, because then the first player will get 12 instead of 9. And since, there is no guarantee or no way to enforce this cooperative solution, it's unlikely to occur. So this game cannot be defined as the prisoner's dilemma, because not all the assumptions are met, but, this situation in particular has something in common. But we will get back to this. Okay, so here you just have the solution, and basically it describes what I've just said. Okay, sorry, give me a second. Okay, that's better. No idea why this happened, so yeah. Okay, another way to solve the game is to apply iterated elimination or successful elimination of dominated strategies. So basically, dominant strategy is a strategy which is the best, regardless strategies played by other players. Dominated strategy is a strategy which is inferior to all the alternatives, or at least one strategy, regardless of the strategies played by other players. Here we distinguish between strong domination, strongly dominated strategies, where each of the possible payoff under strategy X is better than respective payoff under strategy Y. Then Y is strongly dominated, and weakly dominated, where each possible payoff under strategy X is better than or at least good as respective payoff under strategy Y. Then we say that Y is weakly dominated. You will see this in a second. Okay, so consider this game. Here you just have to figure out whether there is any strategy which is inferior or superior in comparison to other strategy, regardless of the moves undertaken by the second player. So for instance, we can compare strategies A and B for the first player. Here, if the second player chooses X, 10 is better than 0. If the second player chooses Y, 5 is better than 4. However, if the second player chooses Z, then 6 is better than 3. So neither of the strategies is dominated by other strategy. So, we cannot say that for sure the first player will never choose strategy A or strategy B. It's not true. It will all depend on the move undertaken by the second player. We can compare strategy A and C. Here, 10 is better than 2, 5 is better than 3, and 3 is better than 2. So, yeah, actually we see that it never makes any sense for the first player to prefer strategy C over strategy A. That's why we start the solution with crossing out strategy C. And you can see it here in this note. Then we can proceed to the second player. We can compare strategy X and Y. So here 4 is better than 3. However, 1 is worse than 6. Again, we cannot say that either of the strategies is dominated by other strategy. It all depends on the move undertaken by the first player. Let's compare X and Z. So here 4 is better than 2, 1 is better than 0. So we can say that it never makes any sense for the second player to choose Z over X. So when X is available, he will never choose Z, that's why we cross it out. Then we can get back to the first player. So here, 10 is better than 0, 5 is better than 4. So after we crossed out this segment of the matrix, B is definitely dominated by A. That's why we can cross strategy B out. And finally, we're left with only 2 cells. And we can see that the second player will never ever prefer Y over X. That's why we cross Y out and we are left with the solution, or Nash equilibrium. Okay, so here you have another example of the game which is called Prisoner's Dilemma. And in this game, there are 2 strategies available to each player. So the story behind this is as follows. 2 friends committed a crime together and they are caught by police. So each of them has 2 options. They can either deny everything, just keep silence, and this option is referred to as cooperate. Or alternatively, they can confess, which basically means telling the police that the other person has committed a crime. So they are to make this decision simultaneously. I don't know, like being locked in separate rooms in police department. That's why we qualify this as simultaneous game, so there is no opportunity for any cooperation for these players. So, take a look. Here, each player has a dominant strategy to confess. Like here, if both of them cooperate, then police can keep them in department for 1 year, and then in the absence of evidence, the police will be forced to let them go. So the respective payoff is 1-1. If the first person decides to confess while the second player keeps silence and cooperates, then the one who confessed is free to go immediately, Like here we have 0 length of the sentence, and the second player will get 15 years of sentence in prison. If the first player decides to cooperate and the second confesses, then cooperating player gets 15 years in prison, and the one who confessed gets 0. He is just free to go immediately. Finally, in both of them confess, they get 5 years each. So please keep in mind that these payoffs stand for the years spent in prison. So basically, less is better in this case. So the key feature of this game is that both players have dominant strategy to confess. So let's analyze it for the first player, for instance. So if the second player decides to cooperate, then it's better for me to confess, because then I'm free to go immediately. If the second player decides to confess, then it's better for me to confess as well, because thanks to this, I will get 5 years instead of 15 years. So for me, it's always better to confess, regardless of what the second player does. And actually, the same applies to the second player. Like for the second player, it's always better to confess, regardless of what the first player does. So on the intercept of those dominant strategies, confess, you have Nash equilibrium, which is 5-5. So each player will get 5 years in prison. Again, keep in mind that this solution is not Pareto efficient. So for both players, it would be better to keep silence, and then each of them will spend just 1 year in prison. So it's impossible to improve their situation simultaneously. However, this is unlikely to occur unless you have some instruments to enforce cooperation. And this is not the topic of this lecture. So consider another example. We have two players, Congress and Federal Reserve, like central bank in the United States. So Congress can choose between budget balance and budget deficit as the fiscal body, and Federal Reserve as the monetary policy body can choose between low interest rates and high interest rates. So if there is a budget deficit and the central bank chooses low interest rates, then Congress will get 4 and Federal Reserve will get 1. If Congress chooses budget balance and Federal Reserve chooses low interest rates, then 3 goes to Congress and 4 gets to Federal Reserve. So you've got the idea. So here your task is to figure out whether any of the players has any dominant strategy and what would be the most adequate response of the second player. Again, if you'd like to do this on your own, put this video on hold, and I'm proceeding with the solution. So, budget deficit is a dominant strategy for Congress, because regardless of the decision made by the central bank, it's always better to have budget deficit. If there are low interest rates, then budget deficit means 4, while balance means 3. If there are high interest rates, then budget deficit means 2 instead of 1. So yeah, budget deficit is a dominant strategy for the Congress. There are no dominant strategies for the Federal Reserve, because here 4 is better than 3 and 1 is better than 2. But actually, even one player having a dominant strategy, will be just enough to solve this game in 2 steps. So Federal Reserve knows that Congress will never ever choose budget balance. It makes no sense. In this case, keeping this information in mind, Federal Reserve can choose low interest rates and get 1, or high interest rates and get 2. So obviously 2 is a better option. That's why here we have resulting Nash equilibrium. It doesn't really matter, by the way, which kind of analysis you apply. You can also do successful iteration of dominated strategies or best response analysis. The resulting Nash equilibrium will be just the same. Again, keep in mind that this is not Pareto efficient outcome. It's possible to improve payoffs of both players simultaneously if we shift to this cell. Like, one associated with combination of budget balance and low interest rates. Okay, when you apply the method of successive elimination of dominated strategies, and now I think I said successful when I analyzed it before. Okay, doesn't really matter. So under successive elimination of dominated strategies, please be aware that in case of weakly dominated strategies, you have a chance to lose some Nash equilibrium. So take a look at this game. So for Rowena, going up will mean getting 0 if the call-in plays left and 1 if the call-in plays right. For down, Rowena will get 1 if call-in plays left and 1 if call-in plays right. So actually for Rowena, the strategy up is weakly dominated by strategy down. Like very informally, it makes no sense for Rowena to choose up over down, because then she will get either worse outcome, either the same outcome. So here we can eliminate this weakly dominated strategy, and as a result you've got 2 Nash equilibria. However, if you solve the same game using best response analysis, you will see that upright is another Nash equilibrium. So when you deal with weakly dominated strategies, using the method of successive iteration of dominated strategies might force you to cut off Nash equilibria which actually exist in this game. So what it implies is that it's always better to double check using best response analysis when you deal with weakly dominated strategies. Okay, so we can try to solve the same we can try to solve simultaneous game with 3 players using the same payoff matrix, but this will require you applying some additional tricks. So here we can get back to the street garden game, which was analyzed during the previous lecture. But now let's assume that all the ladies, I mean Emily, Nina and Talia, make their decisions simultaneously. And in this case, we also assume that, it's possible to differentiate between gardens of the different size. So ranking of outcomes is as follows. Let's analyze it from the perspective of Emily, just for the sake of simplicity, because actually it makes no difference. They make decisions simultaneously, so there is no advantage associated with the sequence of their moves. So for Emily, the worst possible outcome is when she is the only person to contribute. In this case, she has small garden and she has to pay for this. So we assume that this outcome is the worst for her. The second worst outcome is when other players do not contribute and Emily does not contribute as well. So this means no garden, but also this means no necessity to pay for anything. Payoff 3 is assigned to the outcome when one player contributes and Emily does the same. So there are 2 of us to contribute, and 4 if one player contributes and I do not. So in this case there is a small garden and I do not have to pay for this. 5 when 2 other players contribute and I have to contribute as well. And 6 when 2 other players contribute and I do not. Like in this case we have a middle-sized garden which I get for free. So in order to solve this game, because normally for 3 players it will require drawing 3-dimensional table, which would be a complicated task, but we can apply another trick. So for Nina, let's say for Nina, just it does not really matter. You can do the same for Emily or Talia. It's up to you. So let's assume that in one case Nina contributes, and in the second case Nina does not contribute. So Nina has two available options, and we can draw two tables with payoffs, two payoff matrices, depending on whether Nina contributes or whether she does not. Again, if you'd like to practice, put this video on hold, and here is the solution. So Emily is the first player, since she's the role player. This is payoff for Emily. Talia is the second one, and Nina is the third one. So if we assume that Nina contributes, that here we have all three ladies contributing, so all of them get 5. If we assume that Nina contributes, Talia contributes, and Emily does not, then Emily gets 6. She can enjoy the garden for free. And Emily and Talia get 3, just based on this payoff structure. One other player contributes, so do I. There are 2 of us to contribute. And so on and so forth. So I believe you've got the idea. And what you can do is to start solving this using best response analysis, this time only for Emily and Talia. Again, if you'd like to practice, put this video on hold, and here is the solution. Like, if Emily decides to contribute, the optimal option for Talia is not to contribute. If Emily decides not to contribute, then the optimal solution for Talia is to contribute and get 4 instead of 3, and so on and so forth. So if you do the same analysis for those two tables, you will see that there are 2 possible candidates for Nash equilibrium. Like here, NC and C, and here, NC and C as well. So actually Nina is a rational player, we assume her to be a rational player. And she knows that both Emily and Nina have a dominant strategy not to contribute. So she can choose between contributing and then getting 1, or she can choose to contribute. Or she can choose not to contribute and then get 2. So obviously 2 for her is better than 1, so she will prefer the situation when she does not contribute. And here we have the solution, or Nash equilibrium. So Nash equilibrium will occur when neither of the players will contribute. By the way, this is another example of prisoner's dilemma. It's possible to improve situation for these ladies simultaneously. I mean, to this cell or to this cell. Nevertheless, since we're analyzing their optimal strategies and their intercept, the outcome will be when neither of those ladies contribute and they have no garden, but at least they do not have to pay for this. Okay, so it's possible to have multiple Nash equilibria in pure strategies. For instance, consider this game. So the story is like this. 2 people, Harry and Sally, arranged a meeting at the local cafe, but they did not specify whether it's Starbucks or Costa Coffee. So if you solve this game using best response analysis, you will see that there are 2 equilibria when both of them meet in Starbucks and when both of them meet in Costa Coffee, corresponding to the payoff 1-1. Because it's assumed that they will get no utility if they do not meet, if they go to different cafes. So in this game, there is no focal point, no convergence of expectations. Basically, a simple text message, specifying the place of meeting will be enough to have either this or this equilibrium. However, in the absence of cooperation, this is not possible. This is a slightly transformed game In this case, we still have two Nash equilibria, but this equilibrium associated with Costa Coffee, when they meet at Costa Coffee, is associated with higher utility for both players. So keep in mind, there are still two Nash equilibria formally, we still cannot be sure about the outcome of this game, but, having this element when both players know that each of them likes Costa Coffee more than Starbucks might create some convergence of their expectations, just increase probability of their meeting slightly. Although, again, I would like to reinforce this, formally there are still two Nash equilibria and no certainty about actual outcome of this game. Another example of multiple equilibria in pure strategies games is Battle of Sexes, when two people, husband and wife, are to spend evening either in theater or watching hockey. So, as you can see, the husband would definitely prefer hockey while the wife will prefer theater. So again, in this case, we have two equilibria and we cannot be sure about the actual outcome of this game. So to find the single solution, this symmetry of payoffs has to be broken somehow. Probably in reality, it will all depend on which person has a strong willpower, or bargaining power in general. Nevertheless, formally, those two outcomes are equally possible in this case. Unless we assume that players can mix, then the situation can reverse. Again, chicken game, which was discussed during the first lecture, is another example of multiple equilibria in pure strategies. In reality, of course, this is impossible. You cannot have two solutions simultaneously. They cannot go straight and swerve at the same time. However, in order to define the solution, like the single solution of this game has to be transformed somehow. And the ways in which it can be transformed and the implications of these transformations will be discussed when we proceed to strategic moves. Okay, another example, when we have no equilibrium in pure strategies. So here, when you solve this game, try to solve this game using best response analysis, you will see that there is no intercept of the optimal strategies. So here, actually, we have an example of a constant sum or zero-sum game. And in pure strategies, there is simply no solution. Okay, finally, there is additional method to solve constant sum games except of Nash equilibrium. So this method is called minimax method. And the rule is as follows. You always assume that the ultimate aim of the other player is to ensure that your payoff is minimized. So what you do? Like for each of your possible strategies, you have to figure out the worst possible outcome and to choose the strategy with maximum worst possible outcome. Okay, consider this game. Like this game is a constant sum game. In each cell, the sum of payoffs is equal to 6. That's why we can apply minimax method. So if the first player goes up, the worst possible outcome for her is 1 when the second player goes left. So we have it here. If she goes straight, the worst possible outcome is 2. If she goes down, the worst possible outcome is 1. So the first player has to choose straight because under this strategy, her worst possible outcome is actually maximized. For the second player, if she goes left, the worst possible outcome is 4. If she goes middle, the worst possible outcome is 2. If she goes right, the worst possible outcome is 1. So the second player has to choose a strategy with maximum worst possible outcome or 4. So the second player shall choose left, the first player should choose straight, and on the intercept we have the equilibrium. By the way, if you try to solve this game using Nash equilibrium concept, like best response analysis, it will still give you the same result. Okay, so this was it for this topic. Next time we're gonna analyze mixed strategies, and thank you for your attention.